Hi guys. I would like to start today with some very quick reminder of what we talked in the last class. It was about the center of mass. Well, and you already know that the center of mass is very important because it allows us to to represent, or for example, in here, there's to represent the motion or how a force acts in a system of particles or in a body, right? We just once we know the center of mass, we just assume that some maybe a force which is acting on the whole system is just like acting in the center of mass. So that simplifies many calculations and makes everything easy to grasp. So how do you compute it? Well, we know the formula. I think this is the more general one. Like you have many particles, and this like the center of mass is going to be uh, the sum of each particle times each position of the position of each particle times the mass divided by the total mass. And for the three dimensions, you have to do the same for the three components. So then this is when we talk about particles, we use sum, and when we talk about body, we use integration. Okay. So yeah, we talk about this, so we already know this. This is one example of how useful this center of mass is. Like we can now talk about the Newton's second law in a system of particles, in which we can uh, just add like the sum of forces is equal to the mass of the system and times the acceleration which is acting in the center of mass. Well, this is one of the examples is when for example, like when a rocket explodes, because no force is acting on it, the center of mass continues the movement, the trajectory of the movement, even though the particles are just flying away. The center of mass keeps going. Okay. Okay, guys. So now we talk about the linear momentum. This is very important. It's one of the greatest, the important magnitudes in physics. The linear momentum is, well, by definition, is the mass times the velocity, and this allows us to write the Newton's second law in this force in this way, like the sum of the forces are equal to the variation of the momentum with time. You can, well, of course, when we talk about the momentum, the linear momentum of a system of particles, this is like the velocity of the center of mass. Okay. This you can try to do this checkpoint 3. Here that represents p, the linear momentum, versus time, and they ask you which one has greatest force, and here you can see that in 2 and 4 the force is 0, so the linear momentum is constant, and in 1 I think is the strongest force because the steep is the steepest of the slope, and here is descending, so the particle is slowing down, and we have force, but it's not as steep as this. So, well, this is here the answer, which is what did you say, and that's the reason. So again, there's Newton's second law. We can, but this is just like before. We can just write it like the linear momentum in the center of mass. Okay. Another important thing that we can find in this chapter is actually the impulse. Actually important. It's actually not as important as the linear momentum. This this impulses by definition is the definition is the integral of the force over the time. And well, if we use by using this formula, we can quickly derive that this impulse is just the change the delta of the delta p, the change in the linear momentum. This actually is not this concept of impulse is not as useful as linear momentum, but what I say here in the book, and well, you can check all these examples if you want by yourself, but I don't think we are going to go deep on this concept, because this much important concept is the conservation of linear momentum. This conservation is all the conservation laws in physics are extremely important, really important. They have we can use it in many problems. We can use it in many aspects, and these laws is nothing violates these laws. If something says about these conservation laws, it's they haven't found any evidence that it goes against this. One is, of course, conservation of linear momentum. The other is, of course, conservation of energy. And basically, the conservation of linear momentum says that if there is no external force acting on the system, the linear momentum doesn't change. Okay, that is what is called the law of the conservation of linear momentum. We are going to apply this in many problems, many situations, especially when during collisions, which is what they talk about in the part 9.6. They talk about before going further, we have to see what kind of collisions we have. We have what we call the elastic collisions and the inelastic collisions. The elastic collisions are this that they are quite rare. That means that the total kinetic energy of doesn't change. Means that the kinetic energy before the collision is equal to the kinetic energy after the collision, and that usually doesn't happen in the real life, because usually this part of the kinetic energy is maybe absorbed by how hard the body is, or maybe it's changed into heat. So, but this one is very nice approximation. And in the inelastic collisions, we have this part of the energy is transferred. So here the kinetic energy is not conserved, and we have what they call the completely inelastic collision, which is when one object goes inside the other and they stick together. Like this is the change. We're going to see that in this is the case of the ballistic pendulums. That is like you have something like a ball or a body, and you shoot like a gun, and the and how do you call that? Like the bullet goes inside. So this is just typical example of completely inelastic collisions. Okay, so this is this is the how you solve these kind of problems when you have collisions. And as I say, in the inelastic collision, the kinetic energy is not conserved, but since there is no net force acting, no external force, sorry, external force acting on the systems, the momentum is conserved. Okay, you can see here that this is the initial momentum for particle 1 plus the initial momentum of particle 2 is equal to the final momentum of particle 1 plus the final momentum of particle 2. Okay? So this is not that important. This is the other one, the other style that we say that they also can have elastic collisions. And in this case, besides the linear momentum, because it's also conserved because no external forces acting on the system. Besides that, we also have the kinetic energy. Like in this case, we can see that one mass is stopped, and another mass is hit it, and the final position both move with different speeds. And here is how to solve it, but I think you can easily derive from here. There's no need to memorize these kind of things. This was again another elastic collision, but one in front of the other. And when you have two dimensions, well, you have two coordinates, one along the x-axis, along the y-axis for the momentum, because the momentum is a vector, and for the energy is an scalar, so we don't need to use coordinates for this. Okay, you can do the exercise, and well, I hope. I think you already know about collisions, the kind of collisions it is. This is the best way to study this kind of things, is to doing problems, solving problems for the textbook more and more. So I will not talk about much theory about that, because actually it's something when you make when you solve problems that it comes naturally, and we are going to see that in class, and you're going to do exercise about that. So no need to talk too much about these kind of things. Just remember that what I said before, super important thing. Memorize that the linear momentum is conserved, the energy is conserved, and that's it. Okay. So I was saying that this thing in this section of the chapter 9, they make one example, a very interesting example of a system with a mass which is not constant, like a rocket. So again, in this system, there is no external force acting on it, so the momentum is preserved. And they rewrite this like initially the momentum is mass times the velocity here, this mass times velocity, and finally after the final position is that there is any random position afterwards, and I say that the linear momentum is what is the mass, which is the original one, and some change, and the velocity, which also changes. Okay, and that is also you have to have this term, which is the speed. The u is the speed of these products, and also depends on how much mass is lost, well, it's used in these products, and it's negative because it's the change that the change in mass for the product, so it's lower. So anyway, they have to cancel each other. Then we use what is the relative velocity, which is the change on the speed is equal to this velocity of this product that is burning relative to the frame, plus this is the velocity of the rocket relative to the products. These two. This is how you get, and after some computation, they reach to this. This is the final formula. How you compute the change in the velocity is equal to the relative velocity and the logarithms of the masses. Do you wanna? If you're curious of how they compute this, well, this is in the book and in the textbook, and this in chapter 9. Okay. So, well, this is summary means that we're not going to talk more about the this chapter. Now we have to do exercises of especially collisions is very important. Every kind of collision, and they also in the AP test they also make most likely are going to talk about the some um, center of masses. Maybe not computation because they're quite easy, but the definitely center of mass applications and also these collisions. Okay, so we should do a lot of problems and exercise, so we we are going to be sure to master all the topics on this chapter. Okay.